I just heard your ML system design interview is coming up for Meta and Google, and I know you are curious about how these systems actually work. But don't worry, we have got you covered. In this video, we are diving deep into how to design an ML-powered search engine end to end, from ranking algorithms and embeddings to retrieval strategies and real-time feedback loops. So grab your coffee, hit the like button, and let's build an ML search system together. Alright, so how do we even approach a ML system design problem, especially for something like search? Well, the good news is the approach actually follows a logical flow very similar to classic software design problem. The key difference though, we are now thinking about machine learning components like models, data pipelines, feedback loops on top of everything else. The real goal here, especially in interviews, is to show that you can zoom out and design a production level ML system, one that's robust, scalable, and can be deployed as a real service in any company's ML infrastructure. And yes, just like designing backend systems, there is a structure to it, and that's exactly what we are going to break down next. This figure is taken from a very well-known paper in machine learning world, the hidden technical depth in machine learning systems. So the link of this paper is in the description, but you can see like deploying machine learning models is way more than just training a model that performs well on your local machine. In reality, production ML systems like Google are made up of multiple distinct components all working together seamlessly. In this video, we're gonna be diving into these components one by one so you can see exactly what goes on into building a search system powered by machine learning. Alright, so this is super important. If you're wondering how to even tackle an ML system design problem, this is your go-to template. Think of it like a roadmap, step-by-step guide through every major piece you need to cover in your design. So I guess the first thing that you need to do is make sure that you have clear understanding of the problem. Next, rough estimates. Think users, queries per second, latency, all the numbers that influence your design. Then define the metrics. What does success looks like to you in this case? From there, map out the architecture components. Could be data stores, model training, and serving infrastructure, all of it. And of course, don't forget the ML specific part, which is around like how do you collect the data, feature engineering, model development, and offline evaluation. Once your model is ready, think about the prediction service, how it serves online features or online to the user. And finally, the big one, online testing, deployment, scaling, monitoring, and those aspects. This framework keeps you organized and ensures you cover both system design and ML specific challenges. So yeah, let's try to apply this to a search system example. Alright, so let's start with the most important step, problem formulation. Before jumping into models or fancy algorithms, we need to understand like what exactly are we trying to solve, right? In our case, we are designing a search system like Google and Amazon where the goal is simple. Show the most relevant result to the user as soon as possible. The business goal, improve user experience, I guess, drive engagement. And let's be real, we also want to increase the revenue so that the users keeps coming back. So yes, this is the use case and business goal. We need to define the scope. We should check with the interviewer what features does our system need. So some examples of features could be like personalization based on user history. Should we handle autocomplete? And how fast do we need to return the results? Is it 100 milliseconds or less? So this could be an example. Then we need to define the constraints like what are the latency requirements, what are the scale requirements, and are there any constraints on user privacy? And of course there will be. So once you define this, then you also need to understand like or think about like how do we get this data, right? We will need huge amount of user queries, clicks, content metadata, user profiles, assuming that we are anonymizing them. So now we know what we are building. The last question to ask is, do we need ML here? For ranking millions of results, handling personalization, and learning from user feedback, the answer is obviously yes.
Yes!
So our objective becomes predict the most relevant result for every user query. It's a supervised learning algorithm, typically a learning to go setup where we predict relevant score based on features from the query, the user, and the content. Quantity estimation, 1 billion DAU. If that's the case, then let's say they would do 20 10 to 20 searches per day, right? So that means this will be 20 billion requests per day peak, right? So this is the peak. It's basically 20 into 1019 divided by 86000 queries per searches per second, right? And then this will give, it's basically, so 3 into 10 to the 5 queries per second. So this will be the 300,000 queries per second. See, your latency requirements are that it should be under 10 milliseconds, right? If we say data estimation, damn it. So we have, let's say, 100 billion pages to scroll, right? And then if we have 100 billion pages to crawl, each page, let's say 1 KB in size. So this will be how much? If we say data estimation, so 100 petabyte. So then this is 300,000 queries per predictions per second. If we call one model, if there are multiple models, or if it is called sequentially, then it's even bigger scale. So 300,000 predictions per second, definitely not serverless, and definitely not HTTP calls. So I think this is how the estimation could be rough, and it kind of gave you an idea of what we need to do. So we have the requirements and we know the scale. Next is to define what success looks like. So for that, we need to define the right set of metrics. So for this case, I think we can start with the user level metrics. So some metrics I can think of are the click-through rate. So whether the users are clicking on the results we are showing them. Another one is like time to result. How quickly are we returning the results? Ideally, we want it within 10 milliseconds. Query success rate. How often does the user finds what they are looking for in the first attempt? And then dwell time. How long does the user stay after clicking? A good indicator of relevance. So these are some of the user metrics that we need to collect. From the ML perspective, I think we need to measure how well our model ranks the right results. Some common metrics I can think of are mean reciprocal rank. So are the results appearing relevant? Normalized discount cumulative gains. So NDCG, how good is your ranked list overall? Precision at K, recall at K, how many of the top K results are truly relevant? Area under curve, ROC. So useful if we frame this as a binary relevance prediction found problems. This is a 2x2 framework which I generally use to solve any of these problems. It shows how we balance heavy offline computations with real-time speed requirements to build production-grade search system. Components here on the x-axis: retrieval and ranking. So retrieval is the first step, where what we are trying to do is to filter out millions of items down to just few hundreds. So we don't really care about precision here, but speed is something that we need to ensure because we are going through millions of items. The second part of it is ranking, which is the step where we score and order the best ingredients, and that's where the ranking model will come into play. Since we have fewer items, we can add rich features and use more complex model to improve accuracy. In terms of the processing side, there is offline processing and online processing on the y-axis. Offline processing also like batch processing. So what we are trying to do here is to train the models. So we generate vector representations from catalog models for embedding models and ranking model for scoring. Then we build an ANN. So it's not artificial neural network, but it's more like approximate nearest neighbor. So this helps us find similar items quickly and then create a feature store. So apart from these rankings, there is also a feature store that we use, which is storing the user informations or user features and the item features for ranking. On the online side, whenever the user types a query, so what happens in the background is that it's converted into embeddings, but also like we add some kind of pre-processing steps before we do the embedding. So this includes like removing the stop words, stemming, and other NLP tasks that we can perform. So this will generate the embeddings. We can use the same model that we use for on offline training for generating the embeddings, and then using the artificial neural networks or other retrieval methods, we fetch the top k potential matches. So this is basically going through that millions that we talked about. And then feature augmentation, where we add like extra relevant features and metadata on the online side. And then finally, we run the ranking algorithm that returns us the best matching results and their scores. This is a blog post from Elastic, the company behind Elasticsearch. So they kind of gave a good definition here. So it's an algorithm that defines a data point in a dataset that's very close to a given query point, but not necessarily the closest one. So this is an approximate algorithm, but this is a key to nailing fast similarity search because we are doing an approximation here. So it works on the principle of dimensionality reduction, where the goal is to return a higher dimensional data set into a lower dimensional one. An algorithm also leverages clever data structure like indexes. By pre-processing the data into indexes, ANN can navigate the search much quicker. So KD tree is one. KD tree organizes data points in a hierarchical tree structure, partitioning the space on specific dimensions. This enables fast and efficient. This is fine. But while KD trees excel at finding nearest neighbors in a low dimension, they suffer from the curse of dimensionality. That is, where the number of dimensions increases, the space between points explodes. Basically, KD tree doesn't work very well in high dimensional data. Locality, locality sensitive hashing. Locality sensitive hashing is an ANN technique that works by hashing data points into lower dimensional space in a way that cleverly preserves the similarity relationship. This clustering makes them easier to find and allows locality hashing to excel in search massive high dimensional data for both image and text. And that's where, while still returning close enough matches with good accuracy, but keep in mind that locality sensitive hashing might also occasionally produce false positives. So this is the overall algorithm. Take a moment to go over these steps for clarity. What does it? This is the paper that they published few years back on building their ranking as search system. So here, oh yeah, it's here. So this is their overall architecture for the recommending product. In the offline environment, session level user item interactions are mined to construct a weighted bidirectional item graph. The graph is then used to generate item sequences via random walks. Item embeddings are then learned via representation learning. So this is the algorithm they use for embeddings. It's called word to vec skip grab. Finally, with the item embeddings, they get nearest neighbor for each item and store it in their item to item similarity map. This is what they do in the online environment. When the user launches the app, Taobao personalization starts by fetching the latest data the user interacted with. So example, clicks, likes, purchases. These items are then used to retrieve candidates from the eye-to-eye similarity map. The candidates are then passed to the ranking system for ranking via deep neural network before being passed displayed to the user. Another example is the DoorDash architecture. So in their offline store, they use all the restaurants. So this is the document of their restaurants and all the attributes associated with these restaurants, like the metadata. and training data between their models. What models they train, all the models go to the machine learning service. All these are the artifacts that we use. So all the attributes go to the search DB, and all the document store goes to the Elasticsearch, and documents go to Neo4j. It's used as a more knowledge graph here. We'll talk about it later. On the online approach, when the user comes in and submits a query, that query goes through the search service. Now search service has two components, recall and precision. So it, in this first case, it goes through the recall process, and then there are multiple different steps that are done here, mostly NLP steps like spell check. Spell check correct spellings of these, so generally like light spelling checks, and then it goes through the query understanding. So it's basically trying to understand the concept of the query. So it goes through like maybe synonymization as one of the aspect there. An example could be like MACD. Like MACD can map to McDonald's. It can map to uh, McDonald burgers and all those things. Next, the query goes to the query expansion. So this is Neo4j. This is their knowledge graph. Like what is KFC related to? What is McDonald's related to? All that information is kind of stored in the knowledge graph. Over here, they traverse the knowledge graph and finds the most similar item in the knowledge graph and then expands the query. So this is the retrieval step here. So what that means is that when a user searches McDonald's burgers, they're not just gonna return McDonald's, right? They also return some other kind of restaurants, could be like KFC or Burger King or something like that. So this is a general list. The next step is to make the list very precise, and that's where the precision steps comes. So in the candidate set, they runs ranking, which is basically given all the restaurants, which restaurant should be ranked high. Of course, MACD gonna rank higher because that's what the user has entered, but of the remaining restaurants, which one should be ranked the top based on other information like location, ratings, and others. That's what it does here. Also, like similarity of the food the restaurant provides with MACD, and this is the ranker over here. So in both of these cases, they have like offline evaluation and online evaluation. Recall is basically your retrieval, and ranking is your precision here. Architecture. So I would say like we'll have like two systems here, right? And again, so this one is your like online again, right? This is your online system as we saw, and this will be offline here on our axes, right? And this is retrieval, ranking, and this will be retrieval. Architecture. So I would say like embedding service, right? So we need embedding service here. Then there is, once we have this embedding, now we generated the embedding, we need indexing service. So this indexing service could be like getting some user data. There could be a feature stored here, right, of user information. So let's say if there is a user u, so this will be your user information. This is gonna be built here, right? And feature stored here, they store the user information, and then this is the ranking model that will return the results to you. So we got the indexing service, then we got the ranking model that uses this and returns the result. Here is the user information that is coming, and then there could be like product information here, right? So this information can become, and this will go through again. So connect this guy here, and this will go through like embedding model service which we defined earlier, generate the embedding, and then store in the indexing service, and then DB information product catalog embedding service. It's gonna go to indexing service, which is more like an ANN index, right? ANN index, and then in ANN will help us get the right index once this information is retrieved. Maybe we need to store this in somewhere, but ranking model, they will pull the feature store information as well, and then return the best results. Let's look at some of the components in this architecture. So the first one is the query processor. Um, so one of the function of query processor is to correct the spelling, the user type. So there are different ways you can do spell checking. As a machine learning engineer, you can mention edit distance, which is basically how many edits are required to correct a misspelled word. There is also simspell algorithm that you can use, creates like pre-computed data for all these corrected spellings, and then do a O1 lookup on that since it's a hash table. And then there is another important algorithm that you can think about, and people have been using it in LLM as well, is the noisy channel model. So here they are using probability distribution to suggest most likely correction based on user behavior. If you want to use deep learning, then transformers like BERT is a good example. So we saw this already in DoorDash architecture, but query expansion is important because the users might not know the exact keyword to search in the document, right? So we want to find similar words. So what we need here is synonymization. So laptop could be notebook. So you can use a WordNet or custom lexicons. Concept expansion, knowledge graphs or ontologies. That's what they have been using with Neo4j. So Apple MacBook becomes like MacBook Air, MacBook Pro, etc. Embedding based expansion. So what to where can we use? So sofa could be couch, love seat. Or user behavior based expansion. So like click log, search history. So cheap phones is affordable smartphones. So yeah, another technique that you can apply is query relaxation. It's basically just removing some of the stop words, simplifying the intent. So you could like, let's say where to find Nike shoes near me. So Nike shoe store. Or negation handling, not cheap phones as like premium smartphones. Sometimes knowing the intent helps quite a lot, especially with rankings. So an example could be like how does 5G work? That means the user wants to learn or wants to know. The second could be like Starbucks near me. Here the user wants nearby results. So this is local intent. There are multiple approaches that you can do, like rule-based matching, so detecting buy for shopping intent, and then machine learning classifiers you can use like SVM logistic, just deep learning like BERT model. Though not super useful for machine learning system design interviews, but it's definitely important to know what are inverted indexes. So indexes offer like a very fast way to identify which document the word contains, right? So here the key will be your word, and the value will be the list of document IDs or a combination of document IDs and term frequencies in that document. So this allows us to like quickly identify what documents it is present. When you are scaling the system, you can start thinking about like what are the optimization strategies I can apply here. So like you're storing a list of documents now, that could be huge, right? Like there could be millions of documents, billions of documents. So how do you reduce the space? So there is a technique called delta encoding. So rather than storing each document's ID, because ID could be millions, billions, that requires a lot of space. So you could use like a delta encoding where you are actually storing the difference from the first document. There are other techniques like variable byte encoding. So rather than using a fixed 4 byte or 8 byte integers that waste space for like four small numbers, you can use a variable byte encoding. Bitmaps are generally used to say whether the word is present in that document, right? So bitmaps are generally just a yes or no data structure. In this case, for rolling bitmaps can be used, which is basically like very beneficial for sparse data. Another component is candidate generation from the list of billions of products. We try to narrow it down to 10,000. There could be multiple search options here, like lexical search, which is exact match based on the keywords. There are multiple algorithms for it, like BM25, TF-IDF, or you can use data structures like try. Semantic search is searching based on the meaning rather than the keywords. You can use multiple algorithms here too, like dense embeddings, approximate nearest neighbor. On the visual search side, you can, if it is just about visually similar products, then you can use CNN embeddings or object detection. There are also like hybrid search, which are more multimodal based approaches. TF-IDF stands for term frequency inverse document frequency. It's a method used to evaluate how important a word is in a particular document compared to all other documents in a collection. In simple terms, it's a way to find out which words are most significant in a text by considering how often they appear and how rare they are. Breaking it down, so there is TF, which means term frequency. It's a measure of how frequent a word appears in a document. So if the word cat appears 10 times in a 100-word article, then the term frequency for cat will be 10 by 100.1. The more times a word appears, the TF score is higher. Inverse document frequency, or IDF, is a measure how unique or rare a word is across multiple documents. If a word appears in multiple documents, then the IDF score is lower. If it is in lesser documents, then the IDF score is higher. So if cat appears in 1 of 10 documents, the IDF would be higher. That shows that the cat is relatively unique. If the cat appears in all 10 documents, that means the IDF score will be lower because it's common. The TF IDF score is the product of your TF and IDF factors. It helps highlight words that are frequent in a document but not common in many documents, marking them as important. So this is the formula that we use for TF IDF calculation. It's pretty standard. An improvement over TF IDF is BM25, which is a probabilistic ranking algorithm that adds two new parameters, tuning parameter as well as length normalization. So it considered like how often does the query term appears in the document, but at the same time it also considered the length of the document and average length of all the documents. It is better than TF IDF in the sense that BM25 doesn't give excess importance to frequently repeated words. Document length normalization is also happening because longer document doesn't get unfairly boosted in ranking, and then you have like K1 and B are fine-tuned parameters that can help you customize it for your use case. After this step, we have around 100,000 candidates left for our results. The next step could be ranking, so where we can build a model that is a two-stage model. So in the first stage, we can apply some simple algorithms like logistic regression or linear regression or even decision tree, and then reduce that candidate set from 100,000 to around 10,000. And then it comes with more precision when we add like another deep learning based model like the transformer based ranker, could be BERT or T5 or CLIP for multimodal ranking. The features could be like query product similarity like BERT embeddings, visual image similarity, CLIP, and then user signals like click-through rate and engagement. And the goal will be to get the top 100 highly relevant results. This will help us fine-tune our solution and get us very relevant results. If your data is using videos, then you need to convert that. So there are two ways to do that: frame level encoding. In that, you extract embeddings for sample videos frames and then aggregates them, and video level encoding, where you capture entire video as one embedding. For video level encoding, you can use video vision transformer, and for frame level, you can use vision transformers. So generally, as the name says, frame level encodings are much more efficient because they deal with smaller amount of data. It's like a frame. But for if you're putting every single entire video as one embedding, then it's expensive. And then you can combine with video level features because it keeps the temporal properties intact of the video. These are some of the storage options you have to store your embeddings, like FAS, which is your Facebook AI similarity search, and then VBA, which is your vector database that internally does some cosine similarity and Euclidean distance, and then Elasticsearch with dense vectors could be another approach. In my views, I will probably go with the Elasticsearch with dense vector approach, but you are free to choose your own solution. Feature selection and engineering are critical for search and ranking models. So in this case, let's define some of the big actors: user, item, query, document, what else? add, context. Yeah, some of the features types could be like user profile for user, category metadata for items. For query, it will be intent of the query, topic, embeddings. Document will be text, context, content, structure, scores. There could be like cross features that you can generate. In this case, I can think of like query document feature, which will use like TF-IDF and BM25 similarity. Another one could be user item features. So like watch history for a particular user for a particular item, user query features, so query reformation patterns, user context features, feature representations, so converting all the categoricals to one hot encoding, ordinal encoding, so ordered categories, membership level could be an example, frequency encoding like large categories, city names, embeddings, high cardinality data. So if you look at the embeddings, then there could be like text embeddings for which you can use BERT and BERT2vec. For image embeddings, we talked about you can use clip and vision transformer. For graph embeddings, you can use like Node2vec. For user embeddings, you can use collaborative filtering. We can consider this as like a point-wise and pair-wise learning to rank algorithm. In the point-wise learning to rate algorithm, we predict relevance of a single item in isolation. So this can be framed as a binary classification problem. Example, if the probability of relevant given the user and the item, user selects that item, it's 0 when it is not relevant and 1 when it is relevant. So this way we can filter out a lot of the items from 100,000 to just 500. And for this we will be using like use logistic regression or MART. So we'll be using pairwise LTR model for precision ranking. It compares two items to determine relevance. It's a function of user item pairs. Loss function is minimizing the incorrect predictions. There are two models that I can think of that can be used here: lambda mart, which is a tree based model, or lambda rank, which is your neural network based. For metrics, I would suggest a normalized discounted cumulative gain for evaluation. You can read about these models in the link in the description. These are some of the loss functions you can use for different models. In our case, since we use pointwise LTR, which is a binary classification model, so we'll use binary cross entropy as our loss function. And for pairwise LTR, which is a lambda mart function, we'll use contrastive loss. Contrastive loss generally are used in embeddings. I suggest talking to your interviewer about training strategy. There are two approaches you can take. Either you train from scratch, just like in case of CNNs, or you can use a fine-tuning approach where you're using a pre-trained model like BERT or CLIP model. There is another strategy you can take, which is where you're not doing any training like RAG-based pipeline, but that's not required for this case. Search engine, in our case search ranking, we are using fine-tuned BERT or lambda mart, so we will be just using an existing fine-tuned model, or for image search it will be a fine-tuned clip model. Then we can also talk about offline and online training. Offline training is basically training the model every day or every month, right? So it's done offline. It's mostly trained on historical data. But let's say if you have real-time data and you want to train the model continuously, then online training is the way to go. Online training means that Instead of retraining a model offline or historical data and deploying it periodically, the model is continuously updated on real-time data streams. So this way, the model can adapt quickly to changes and personalization on user behavior, personalization for user behavior. An example use case will be like if a user searches running shoes and clicks on Nike shoes, the system immediately learns and boosts Nike for similar queries. So this is the idea behind online training. So there could be like two kinds of online training: real-time streaming updates. So true online training, the model updates its parameter immediately when new data arrives. It does not require full training, so instead you just updates the or adjusts the weight incrementally based on new interactions. The example model could be like online SGD, or follow the regularized reader, online Bayesian models, online LDA, or those. The other could be periodic mini batch updates near real time. So this could be like every 10 minutes, 1 hour. The idea is that you have a lightweight model that is trained on recent data and updates the main model. And the main model basically updates like in that frequency, more efficient for deep learning models as that cannot update weight on the fly. For example, search ranking update could be done every hour. The ranking model updates based on new clicks, searches, and purchases. Let's talk about evaluation metrics. So NDCG is a very good metrics in this case. So what the idea here is that measure ranking quality. So positive sentiment, lambda mart could be using NDCG as a matrix. You can use mean average precision evaluates ranking performance for multiple queries. CTR measure user engagement. ROC AUC evaluates binary classifier, like in our case with a smaller model that we used, that can be evaluated with binary classifier. Recall at K measures how many relevant results appear in the top K results. So our evaluation uses lambda mart, which can be done using NDCG, which we talked about. And user CTR uplift can be used to measure real world impact of ranking performance. For predictions, let's talk about predictions. So there are batch predictions or online predictions. So latency could be high, like hours or days, low milliseconds. So it just depends on your use case. If you're using an online prediction that is real time, then you need to use serving like which has a very low latency. So you can use TensorFlow serving, fast APIs. You can use SageMaker endpoints. You can use all those cloud providers, REST APIs. But if you're using batch inferencing, then Spark or Airflow is gonna do your job. So let's in this case we have around, so we initially just did the rough ballpark numbers, and it came to be around 300,000 predictions per second for search scale, which is quite a lot. And if you look at the support you can have on SageMaker, generally SageMaker response time is around 100 to 10 milliseconds. But let's say if we need something even faster than that, then edge computing is the way to go for us. It offers very low latency and data stays on the device, so you don't move the data out of the device. And compute constraints, so limited memory, battery power. So that's the problem with edge computing, because you can have only lightweight models. So some of the frameworks that you can use is TensorFlow Lite, Onyx Runtime, or ML Kit from Google, which is mostly used for mobile ML APIs. There are compression techniques you can use when you're using like edge computing, because you need to make the model lightweight. So you can use quantization, so convert 32-bit floating point numbers to 8-bit integers. Pruning, remove unimportant neurons or weights. Knowledge distillation, train a small model to mimic a large one. Or you can use a factorization approach where you decompose larger metrics into smaller ones. This is very important. You should know each of these like thoroughly, what these refers to. Though it depends on the interviewer, but you can talk about A/B testing. The steps involved are, you need to define what metrics you are trying to improve. So it could be CTR or dwell time. Then you need to split the users in these two groups. So it could be a random split or it could follow a convention. And then you need to make sure that there is a null hypothesis. So assume no difference between A and B. And then you run the experiment. So serve A to one group, serve B to another group. After you do that, you analyze the results. For that, you can run statistical tests like t-test, chi-square, Bayesian, and then you make a decision. So in A/B testing, you have a fixed group, but if you want to run these experiment dynamically, you can use multi-arm bandits. We have a separate video for it. You can take a look. And the idea behind multi-arm bandits is to dynamically run these experiments. Let's talk about monitoring and scaling. Scaling is very important because at the scale of search, we will need some of the infrastructure that support that many users. We are getting 400,000 requests per second, so we need distributed servers. So use multiple servers to handle more requests. Load balancing has to be done. Sharding, we can talk about, and application strategies, caching. For scaling machine learning systems, there is distributed ML. You can talk about data parallelism, where each machine trains on different batches of data. So basically, we're splitting the data across multiple machines. And model parallelism, where we split large models across multiple GPUs. So we have a separate video on these two topics. You can take a look. The link is in the description. Distributed training, so you can use synchronous SGD, where all workers update weights at the same time to ensure consistency, but slower, because this is impacted by the slowest worker. And asynchronous SGD, workers update weights independently, faster, but risk of stale updates. If you're building a large language model, a pretty high big model, so then you need both model and data parallelism to train efficiently. For monitoring, there are different kind of metrics you need to monitor. Software metrics like latency, server time, CPU, GPU usage. So these could be measured based on your instance performance, or based on your machine that you're using for inferencing. So AWS automatically supports this. ML metrics, so you need to have accuracy, precision, recall, or some of the ways to monitor these ML metrics. A/B test results you need to monitor, and then drift detection. So it could be covariate, label, concept shift. So you can talk about how do you measure the drifts. It could be data drift or model drift. Yeah, so that's other thing. I guess that's it, guys. We covered most of the topics that are required for ML system design interview. I would suggest sticking to the template that I shared earlier in the slides, but it also depends on your interviewer what they want you to focus on. Yeah, that's it. Let me know in the comments how did you find the video. Is there any topic that I missed in this video, or you want me to cover in the next video? Let me know, and I will see you in the next video.